Hello guys, welcome to today's class. In today's class, we'll be discussing binomial expansion, and in this class we'll learn how to expand various binomial expressions. Now if this is your first time seeing my video, do well to like and subscribe so you get notifications when I upload new videos. Alright, so let's go to binomial expansion. What is a binomial expression? A binomial expression is any term given the form a plus b to the power of n. When you have two terms by given to a raised to a given index or raised to a given power, is called a binomial expression. An expression which has two terms raised to a given index or raised to a given power is called a binomial expression. And every binomial expression can be expanded despite the nature of the power or the nature of the index. The index can be a positive integer, could be a negative integer, could be even a fractional index. So when you have a binomial expression of this form, you can expand it using the binomial expansion theorem. Now, why do we need this binomial expansion theorem? What is the importance of this binomial expansion theorem? Now, let's say you have an expression of this form, a plus b to a given index. For example, if I have a plus b to the power of 0, we know this is definitely 1 because any expression raised to power 0 is 1. Now, let's say you have a plus b to power 1. Anything raised to power 1 is the given expression. So this will be simply a plus b. Anything raised to power 1 is the same value. Now, if you have a plus b to power 2, this is more like combining this expression in two forms, in two brackets. So I have a plus b bracket a plus b, and then you expand this. Okay, let's try out this expansion. I just want to show you the importance of the binomial expansion theorem, which we'll consider in this class. A plus b into a plus b, if you want to expand it, this is a times a, you have a squared, plus a times b, you have ab, plus b times a, you have ab, plus b times b, you have b squared. And you go on to simplify this expansion. You have a squared plus ab, you have 2ab, then plus b squared. Now let's say you have a plus b to the power of 3, a plus b to the power of 3. Now this is more like combining this expression a plus b into three brackets, into three forms. So I have a plus b bracket a plus b bracket a plus b. And we can first of all combine these two and then open up with this one, right? Already we have this as a plus b to power 2, right? This is the same as this one, and then expand to a plus b. Already this expansion has given us a squared plus 2ab plus b squared. All right, so this is for a plus b to power 2, and then we're expanding it against a plus b. Now, if we do that, this is a squared times a, we have a cubed, plus a squared times b, we have a squared b, plus 2ab times a, we have 2a squared b, plus 2ab times b, we have 2ab squared, plus this also opens up this, b squared times a, you have ab squared, plus b squared times b, you have b cubed. All right, so if we work this out, we have a cubed plus a squared b plus 2a squared b, we have 3a squared b, plus 2ab squared plus ab squared, we have 3ab squared plus b3. Now, I believe you are conversant with this form of expansion where you open brackets. Depending on the index here, you open multiple brackets. If we have to power 4, we open about 4 brackets. Now, imagine you want to expand something like this, a plus b to power 12. Definitely, you understand that we have to open about 12, we have to combine in 12 places. We have to open 12 brackets, and that will be difficult to handle because the value will be so large that even when you know what you are doing, you might actually end up making a mistake here. So because of this difficulty in expanding higher powers like this, or even expanding, let's say a plus b to power 1 over 3, how do you expand this? How many brackets do you open? Because of this difficulty in expanding powers of this nature too, that's why we use the binomial expansion theorem. The binomial expansion theorem shows you how to expand any form of binomial expression, whether fractional or very high positive integer, or in fact even negative index. We can use binomial expansion to expand those binomial expressions. So that is the importance of binomial expansion theorem. It allows us to expound any binomial expression to any index at all, and it makes the expansion very easy to tackle. Now let's get into the binomial expansion theorem and see how it works. Now let's consider the binomial theorem and see how it works. Now the binomial theorem states that if you have an expression a plus b to power n, that this is equal to the summation n combination r, a raised to power n minus r, b raised to power r, where r runs from 0 to n. Now, this is the formula, this is the binomial theorem. Now, when you have any binomial expression of this form raised to a given index, that it is a summation of terms, where you have a combination of terms with n combination r, a raised to power n minus r, b raised to power r, and this r runs from 0 to n. Now, we'll see a practical instance of this. Let's expand this and see what it looks like. Okay, so if I expand this, this is equal to n combination r. This is n combination. The first r starts from 0. R starts from 0. So I have n combination 0, a raised to power n minus 0, b raised to power 0. The formula says that it is a combination of terms. It's a summation of terms. So this is the first term plus, because of summation, I have a plus here. N combination r runs from 0 to n. So after 0, the next one is 1. A raised to power n minus 1, b raised to power 1, plus n combination. After 0, we have 1, we have 2. A raised to power n minus r at this point is 2. B raised to power r at this point is 2. And this summation continues till the power of n. So I have plus dot 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 plus n combination n, a raised to power n minus n, b raised to power n. Right. So this is just the expansion of every binomial expression. That it is a summation of n combination r, a raised to power n minus r, b raised to power r, where r starts from 0 to n. Now, if we simplify this, this gives us n combination 0, a raised to power n minus 0 is n, and b raised to power 0 is 1, plus n combination 1, a raised to power n minus 1, b raised to power 1, and b raised to power 1 is b, right? So we have plus n combination 2, a raised to power n minus 2, b raised to power 2, plus dot 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 dot, plus n combination n, a raised to power n minus n is a raised to power 0, right? B raised to power n. Okay, so let's just keep this as b raised to power 0. Let's keep it at that point first, b raised to power 0. Okay, now the expansion is simple, that if you have any binomial expression, that it is just a summation of terms, where the first term takes highest power n, because the highest power here is n. The first term takes n, the second terms start from 0, the power start from 0, plus you subtract 1 from the power of the first term from here, so n, the next one will be n minus 1, where this one increases by 1. So the power here, as it goes down, reduces by 1, n minus 1, n minus 2, n minus 3, till at the final point, a becomes raised to power 0. Why the second term b start from power 0, power 1, power 2 till power n. It's just about knowing the pattern and you are good to go. Now look at the combination. 0, 1, 2, 3 till n. Now the question you might be asking is, why this formula? Why the combination? Now from when we started earlier, from the idea when you have, say, a plus b to power 3, for example, to expand this, we need to combine it in 3 brackets, right? We'll do something like this. For the elementary process, we'll say a plus b, bracket a plus b, bracket a plus b. This is how the expansion works normally. So we combine in 3 brackets. So that same principle is applied there. It's a combination of terms, of these terms. So that's why we have combination here. That's why we have combinations. We are combining into 3 brackets, into 3 forms. That's why the combination at this point is n combination 3. You have up to power 3 because of this. If you are considering something like this, you combine into 3 forms. That's how we deal with combinations. But from the formula, you start combining from 0. The combination start from 0, 1, 2, and ends at 3 for this particular one. Okay, and it's a summation because by the time you expand this, you see this plus this plus this, just like we did when we started this video. That's why there is a summation. And you see the powers on each of the terms too. All right, now let's see a practical example here. Let's look at this practical example here. So on the body we have binomial expansion, positive integer index. Yes, the first binomial expansion we want to consider is expansion involving positive integer index. Like I said earlier, the index can be of different forms. It could be a positive integer, it could be a negative integer, it could be fractional, right? These are the 3 different type of index we'll be considering. Either a positive integer index or a negative integer index or a fractional integer index. And the approaches are a bit different. The approach on positive integer index is a bit different from the negative and fractional integer index. Fractional index rather, not fractional integer index, fractional index. So now let's see how the positive integer index works. I have an exercise here. Expand the following: a plus b to power 4, a plus b to power 6. They are very basic example, and I'm just using this example to make sure you understand the concept of binomial expansion or the binomial theorem. Okay, so let's start with the first one. A plus b to the power of 4. Now this power, this index is positive. It's a positive integer index. So we can directly use this formula here, the Binomial Theorem Formula, and expand. Now, but let's just work this out to show you how simple the formula is. From the formula, we have that you have to combine, you have to make a summation of this, right? A summation of terms, and you have combinations of terms. So the power here, from here, n here is 4 definitely. So we'll say 4 combination 0. We are going to combine this in 4 brackets. That's just the idea. We're combining in 4 brackets, 4 combinations. We're going to make 4 combinations, right? But we're starting from 0. That's just the idea. So 4 combination 0, the first term A will be raised to the highest power 4, and the second term B will be raised to the lowest power 0. If you're able to get this first term, this first setup, you are good to go. So let's look at it again. If I have a plus b to the power of 4, that it is equal to the first term. It's a summation of terms where you make combinations up to 4 terms. Now, 4 combination 0, a takes the highest power, b takes the lowest power, plus 4 combination 1. Remember we said arrow runs from 0 to n, and in this case n is 4. So we have 0, 1, 2, 3, 4. So we have 4 combination 1, a raised to power 3, b raised to power 1. Now look at the trick here. Look at the pattern here. The first term in the first term of this, in this first term takes power 4, takes the highest power. In the second term, it reduced by 1. Why this one takes the lowest power? In the next term, it reduces by 1. It increases by 1 rather. So we have a to power 4, here a to power 3, b to power 0, b to power 1, plus 4 combination 2, a raised to power 1. If you reduce this one by 1, you have 2. And then if you increase this one by 1, you have 2. Right. Now, plus, we have 4 combination 0, 1, 2. This will be 3. Then A, 4, 3, 2 to power 1. B, 0, 1, 2, 3. Right. This is the next term. Plus 4 combination 4. Our row runs from 0 to n. 0, 1, 2, 3, 4. N is 4. Right. So the next term, the first term here, which is A, will be raised to power 0 because from 0 it draws by 1, and then B will be raised to power 4. And this is where it ends because it runs from 0 to n. We cannot go to 5 because we've already exhausted the highest power of n, which is this. So you see the pattern is very simple. It's very simple. A, the first term takes the highest power. Here, it reduces by 1, 3, 2, 1, 0. While B takes the lowest power, 0, it increases by 1. So this increases by 1, increases by 1, increases by 1, and gets to the highest power. It's just a very simple process. So that's what the formula says here. That n minus r, a raised to n minus 0, n minus 1, n minus 2, n minus till n minus n. Why b? B, you add 1, 1, 2, 3 till n. It's a very simple process, right? So from this, you can now simplify. Now let's try to simplify this. You can use your calculator to perform 4 combination 0, but in the course of learning this binomial expansion, I will teach you how to solve combinations. I will teach you the concept of combination, so you can manually solve combination without using a calculator. But for now, let's just let me show you how to solve combinations without your calculator. All right, let's consider how to solve combinations. So I have the combination rule here. So if I have n combination r, it is equal to n factorial all over r factorial n minus r factorial. So this is because we want to learn how to solve combinations here. You have 4 combination 0, 4 combination 3, and all the combinations. So how do we solve combinations? N combination r is equal to n factorial all over r factorial, then n minus r factorial. Now, what is factorial? What is the concept of factorial? If you have 6 factorial, 6 factorial, this simply means 6 times 5 times 4 times 3 times 2 times 1. This is what factorial means. The multiplication of numbers of this particular number by reducing each of them by 1. 6, reduce 6 by 1, you have 5. Reduce 5 by 1, you have 4. Reduce 4 by 1, you have 3. That's a factorial. Right. I have 4 factorial is 4 times 3 times 2 times 1. This is factorial. Okay, so we can perform different operations with factorials. We can do, let's say, 6 factorial divided by 4 factorial. For example, this will be, like we said, this is 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. Now you can see that the whole of this can be divided by this, and you just have 6 times 5, which is 30. Alright, so you can perform different operations with factorial. You can do division of factorial, you can do addition of factorial, you can do multiplication of factorials, and so on. Now, but there is something I want to show you, something interesting about factorial. So if I have 6 factorial divided by 4 factorial, I can keep this at 6 times 5 times 4 factorial, believing that this 4 factorial is the same thing as this 4 factorial down. Because if you look at this, from this point, 4 times 3 times 2 times 1 cleared out 4 times 3 times 2 times 1. So this is 4 factorial up here, 4 factorial down here. So you don't necessarily need to write out all the expressions as long as you have an identical factorial down here. So 4 factorial clears this. And this is simple as 6 times 5, which is 30. So if you have large numbers, say 100 factorial, divided by, say, 98 factorial. You don't need to write out the whole of the 100 factorial. You can simply say this is 100 times 99 times 98 factorial all over 98 factorial. Believing that this 98 factorial will clear out this 98 factorial, and if you do that, this cancels this, so you have 100 times 99, which you have 9,900. And this is how you solve your factorial. So the concept is simple, that when you have a factorial, just write the number, reduce it down, and multiply it through. That's the concept of factorial. So let's come back to our combination rule. So if I have, now let me point this out. There are standard factorials you should note. They are standard factorial. The standard factorials are 0 factorial is equal to 1, and 1 factorial is equal to 1. These are the two standard factorials. That 0 factorial is 1, 1 factorial is 1. So anything other than this, say 2 factorial is 2 times 1, 3 factorial 3 times 2 times 1, and so on. But 0 factorial and 1 factorial are the standard factorial, which gives you 1 and 1. Okay, let's come back to our combination. So let's solve something like 4 combination 0. So if I have 4 combination 0 here, so like we have on the formula for the rule, we have n combination r is equal to n factorial. In this case, our n is 4, our r is what? 0. So following the formula, we have 4 factorial over 0 factorial 4 minus 0 factorial. And this gives us 4 factorial, right? 0 factorial is 1. From the standard factorial, 0 factorial is 1. 4 minus 0 is 4. Then this factorial. So definitely, we don't need to expand this out because we are seeing 4 factorial here, 4 factorial here. So this is 1 over 1. 4 divided by 4 factorial divided by 4 factorial is 1. So we have 1 down here. And this is equal to 1. So this shows that 4 combination 0 is 1, right? 4 combination 0 is 1. And that tells you that any number combination 0 is 1. 6 combination 0 is 1. 100 combination 0 is 1. Any number at all combination 0 is 1. Right. Now let's see more examples here. Let's try out the next one. We've done 4 combination 0. We have 1. Let's try out 4 combination 1. So let's say 4 combination 1. From the combination rule, we have 4 factorial, which is n factorial. Our r is 1. Here n equal to 4. R equal to 1, right? So our r is 1 factorial, r factorial. So we have 4 minus 1 factorial. And this gives us, let's just keep 4 factorial first. We have 1 factorial. Let's simplify the one in bracket. We have 4 minus 1. We have 3 factorial. Okay, so this simply means 4 times 3 factorial. I would not want to finish up this. I would not want to spread this down because I'm already seeing 3 factorial down here. And I know that it will clear this one. So I just stop it at 3 factorial. So I have 1 factorial, 3 factorial. I definitely know that this will clear this. So I have 4 over 1 factorial. This is 4 over 1 factorial is 1. 4 over 1 is 4. Yeah. And that shows you that this is directly from the fact that n combination 1 is equal to n. Any number combination 1 is equal to that number. 10 combination 1 is 10. 100 combination 1 is 100. I will show you the rule. I'll show you the proof of from the value n, how to solve n combination 1, n combination 0, n combination any number. But for now, let's pay attention to how to solve these particular values, which is 4 combination 0, 4 combination 1, 4 combination 2. I would urge you to try out 4 combination 2, and then 4 combination 3, and 4 combination 4. Let me give you some time to try that out. Okay, believing you've tried it out, let's just follow and see if what you did is exactly what I have here. So the next one is 4 combination 2. I have 4 factorial over 2 factorial into 4 minus 2 factorial. This is 4 factorial. 2 factorial is, this is 2 factorial. 4 minus 2 is 2. This is also 2 factorial. If you go on with this is 4 times 3 times 2 factorial. This is 2 factorial, 2 factorial. One of them clears this. I have 4 times 3 over 2 times 1. This is 12 over 2, and this gives me 6. So 4 combination 2 is 6. I hope that's what you got. So we can do the same for 4 combination 3. 4 combination 3 is 4 factorial over 3 factorial 4 minus 3 factorial, following the rule, the combination rule. And this gives us 4 factorial over 3 factorial. 4 minus 3 is 1 factorial. So this gives us 4 times 3 factorial. I'm just going to drop it at 3 factorial because I'm seeing 3 factorial down. All over 3 factorial, 1 factorial. This cancels this. I have 4 over 1 factorial, which is 4 over 1, which is 4. So 4 combination 3 is 4. In fact, there is a rule that n combination m minus 1 is equal to n. So when I have n 4 combination 3, 3 is 4 less 1. So when you have 4 minus 1 is 3. So any combination of this form, n combination n minus 1 gives you back your n. So something like 6 combination 5 is 6. 7 combination 6 is 7. Something like that. So it's a base. It's a rule in combination. Okay, so this gives us 4. And the last one for this, we've done 4 combination 3. The last one is 4 combination 4. 4 combination 4. This is 4 factorial over over 4 factorial. Following this rule, our array is still 4. 4 minus 4 factorial. This is 4 factorial. This is 4 factorial. 4 minus 4 is 0 factorial. This is 4 factorial. So this cancels this. I have 1 over 0 factorial. This is 1 over 1. Remember, 0 factorial is 1, like I told you earlier. And this gives you 1. So 4 combination 4 is 1. And it's a general rule that n combination n is equal to 1. Any number combination itself is 1. So this is just a brief understanding of combination rule. And I believe with this, you can solve any combination you encounter. Right? So let's come back to this. We've already done 4 combination 0. And from what we have, 4 combination 0 is 1. We have 1. A to the power of 4 is a to the power of 4. B to the power 0 is 1. Plus 4 combination 1 like we did. 4 combination 1 is 4. Which we did here. 4 combination 1 is 4. So we have 4 here. This dot here means times. So I'm multiplying. All of these are multiplied. So I'm multiplying, right? So a to the power 3 is a to the power 3 times b to the power 1 is b plus 4 combination 2 like we did is 6. 4 combination 2 is 6. So I have 6 here. A to the power 2, b to the power 2 plus 4 combination 3 like we did is 4. Right, so we have 4. A to the power 1 is a, b to the power 3. So I'm just following up on this. Then plus, I'm on this point now. 4 combination 4 is 1, right? So I have 1. A to the power 0 is 1. N to the power 0 is 1 definitely. And then b to the power 4 is b to the power 4 here. If we continue this, if we multiply 1 times a to the power 4 times 1 is a to the power 4. Plus 4 times a to the power 3 times b is 4a cubed b plus 6. If you multiply this, this is 6a squared b squared plus this is 4ab cubed plus multiply all of this, I have b to the power 4. And this is the expansion of this problem. All right, using our binomial expansion theorem for positive integer index. Now let's try the next example and see how it's done. Let's look at the next example. A plus b to the power of 6, right? A plus b to the power of 6. And let's approach it directly. And I want you to understand the approach thoroughly, right? Now, we have a plus b to the power 6. From the binomial theorem, we are supposed to make 6 combinations, right? But this 6 combination will start combining from 0, right? The first power here is 6. So let's follow the rule. So we have 6 combination 0. I do not want you to always keep writing the formula, the binomial expansion formula, before you can do this expansion. I want you to see a pattern and work with that pattern, right? So when you have an expression like this, a plus b raised to the power 6, you don't need to rewrite the formula, the binomial expansion formula, before you can compute the expansion. Just go direct. 6 combination, start the combination from 0. 6 combination 0. The first term A takes the highest power. The second term B takes the lowest power. If you can get this first setup, then you are good to go. The next setup is just about adding summations, running this 0, 1, 2, 3, 4, 5, 6, alternating the powers of the terms A and B. So what I mean is this, plus 6 combination from 0, I have 1. A, we remove 1 from this, I have 5. So A drops by 1, while B increases by 1. So B will be raised to power 1. A to power 6, A to power 5, B to power 0, B to power 1. Plus, after 6 combination 1, you have 6 combination 2. A raised to power, from 5 it drops to 4. B from 1 increases to 2. And you continue. After 6 combination 2, the next time will be 6 combination 3. A, from 4, it will drop to 3. B, from 2, it increases by 3. So you see the alternation there. A reduces, B increases. And the arrow here runs from 0 till that power 6. All right, so plus 6 combination 4. From 3, it moves to 4. A reduces by 1, I have 2. B increases, I have 4. Plus 6 combination 5. A reduces, I have 1. B increases, I have 5. And remember, this combination progresses till I have 6 down here. So plus 6 combination 6. This is where it will end. This is where it will end, 6 combination 6. Because arrow runs from 0 to n to the power 6. All right, so this is A. A reduces by 1, I have 0. B increases by 1, I have this. And you see something interesting about the terms. Is the highest power of A from the first time is 6. While the highest power of A on the last time is 0. The highest power of B on the first time is 0. The highest power of B on the last time is 6. So A drops from 6 to 0, while B moves from 0 to 6. And this is the last time, and that's where you stop. All right, the rest part is just on solving your combinations and doing your arithmetic, simplifying the expressions. Okay, so let's continue with this. How do we solve 6 combination 0? Like I told you, any number combination 0 is 1 rather. 6 combination 0 is 1. N combination 0 is 1. We can see it from this example. 4 combination 0, we have it as 1 here. So 6 combination 0 is 1. A to the power of 6, we have A to the power of 6 times B raised to the power 0 is 1. All right. I believe that's okay. Then 6 combination 1, like I told you guys, any number combination 1 is that number. N combination 1 is n. So 6 combination 1 is 6. This is A to the power of 5. This is B to the power 1, which is B, right? So I've simplified this. So let's go to the next one. 6 combination 2. Let's just solve that out. 6 combination 2. Okay, let's see. This is 6 combination 2. We have 6 factorial over 2 factorial 6 minus 2. So I'm working this out from the combination rule, which we did earlier. So, and this is 6 factorial. Let's just simplify this. This is 2 factorial. 6 minus 2 is 4 factorial. This is, okay, let me do it here. This is 6 times 5 times 4 factorial. I'm going to drop it at 4 factorial because I'm seeing 4 factorial here. All over 2 factorial, 4 factorial. This clears this. So I have 6 times 5 divided by 2. Because 2 factorial is 2 times 1. So definitely this is 30 divided by 2, which is 15, right? All right. So 6 combination 2 is 15. Next I have A to the power 4 plus B squared. Plus the next one is 6 combination 3. Let's resolve 6 combination 3. You can give it a try and see what you get. Do 6 combination 3. Also try out 6 combination 4. Already I know that 6 combination 5 will be 6 because n combination n minus 1 is n. So 6 combination 5 will be 6. 6 combination 6 will be 1. So try out 6 combination 3 and 6 combination 4. Alright, there's also a concept of the Pascal triangle which you can use to compute these two. Maybe in next example, I would give the idea of Pascal triangle so you understand that concept too. But it's important to know how combination works and how to simplify them. Pascal triangle is just a product of this combination rule that's already solved out. So you can try this out and see. So let's try out 6 combination 3. So this is 6 factorial over 3 factorial 6 minus 3 factorial. That n combination r is equal to n factorial all over r factorial into n minus r factorial. So this gives us 6 factorial over 3 factorial. 6 minus 3 is 3 factorial. And this gives us 6 times 5 times 4 times 3 factorial all over 3 factorial, 3 factorial. This clears this. I will have here 6 times 5 times 4 all over 3 times 3 factorial left here is 3 times 2 times 1. Okay, so simplifying this, 3 go here. I have 2 times 5. 2 go here. I have, this is 2 here, 3, 2 here. All right, so this is 2 times 5 times 2. So I have 10 times 2, I have 20. So 6 combination 3 is 20, right? So I have 20 here for 6 combination 3, then a to power 3, b to power 3. Now let's also do 6 combination 4. I suppose that should be 15, but let's just be sure. 6 combination 4, this is 6 factorial, 4 factorial, 6 minus 4 factorial. This is 6 factorial, 4 factorial, 2 factorial. This gives us 6 times 5 times 4 factorial all over 4 factorial, 2 factorial. This clears this. I have 6. This is 30 divided by 2 is 15, right? Okay, so we have plus, okay, let me write it down here. That's for 6 combination 4. I have 15, then a squared b to power 4 plus 6 combination 5 is 6, a to power 1 is a, then b to power 5 plus 6 combination 6 is 1, a to power 0 is 1, then b to power 6. So this is the simplification. This is the simplification of the combinations. Now let's simplify all these multiplications here. So 1 times a to power 6 times 1 is a to power 6. Plus if I multiply all of this, I have 6 a to power 5b plus this is 15 a to power 4b squared plus this is 20 a to power 3b3 plus this is 15 a squared b to power 4 plus this is 6ab5 plus b6. And this is our expansion of that problem, a plus b to power 6. Now, without this binomial expansion theorem, without this theorem, if you were doing your normal opening of bracket, it might be confusing and you end up making a mistake. Now, imagine you are doing something like a plus b to power 20. You know how complex that can be if you are opening up brackets and you're expanding. That's why binomial expansion theorem is important to know. And this is just how it is. As long as you know how to perform your combinations, you can do this. Now, Pascal triangle also works fine, depending on what you are doing, depending on the type of expansion you are doing, especially when it's a positive integer. You can also use Pascal triangle. Maybe in the next example, I will try using the Pascal triangle and show you how it works. All right, let's understand the concept of Pascal triangle. Now, Pascal triangle is basically for the coefficients of the expansion of the binomial expression when you expand them. Pascal triangle gives you the coefficients of those of the expansion, right? Now, let's see how it works. Let's say it works. So let's say I have a plus b to power 0. We know that anything raised to power 0 is 1, right? 1. So this gives you to this. Now let's say I have a plus b to power 1. So Pascal triangle says, definitely the coefficient here will be 1, 1. So what we are saying is, if I have a plus b to power 0, definitely is 1. The answer is 1. Any raised to power 0 is 1. Now if I have a plus b raised to power 1, is still the same thing as a plus b, right? But the fact is, the coefficient here is 1. The coefficient here is 1. So what Pascal triangle gives you is the coefficient of the terms in that expansion. Alright, so the coefficient here is 1, 1. So Pascal triangle says drop 1, 1. So that's for this. If I have a plus b to power 2, so I'll drop 1 here. So this is, I'll drop 1 here. 1 plus 1 is 2. Now I'll drop 1. It continues this way. I'll drop 1 here. 2 plus 1 is 3. 1 plus 2 is 3. Then I'll drop 1. It continues that way. I'll drop 1 here. 3 plus 1 is 4. 3 plus 3 is 6. 1 plus 3 is 4. I drop 1. I can keep on building this as it goes. So that's what Pascal triangle does. It gives you the coefficient of this binomial expression. So this is more like for a plus b to power 3. That will be the coefficient of each of the terms of the expansion. For this one, this will be a plus b to power 4. This will be the coefficient of the expansion, of the terms in the expansion. And it goes on. Look at how it's being built. You have 1 here, drop 1, 1. And then at the end, drop 1. 1 plus 1 is 2. You are done with this. You drop 1. Drop 1. 2 plus 1 is 3. 1 plus 2 is 3. You are done with this. You drop 1. Drop 1. 3 plus 1 is 4. 3 plus 3 is 6. 1 plus 3 is 4. You are done. Drop 1. The next one will also be 1. 4 plus 1 is 5. 6 plus 4 is 10. 4 plus 6 is 10. 1 plus 4 is 5. Drop 1. And it continues that way. But you need to understand that they are all coefficients of these expressions, of these powers. So you should understand when to use them. You should understand when to use them. For example, let's just say I have, let's expand, say, a plus b to power 5. For example, a plus b to power 5. In this case, if I want to use Pascal triangle, I will not be doing the combinations anymore. I will not be doing the combinations. What I just need to focus on is that a will be raised to power 5, b will be raised to power 0. The normal alternating pattern of this a and b without the combination anymore. Normally, I'm supposed to say 5 combination 0, but I'm leaving the combination. So this is more like there is a coefficient here. There will be a coefficient here plus there will be a coefficient here. I will leave the coefficient. Then say a to power, this draws by 1, I have 4. B increases by 1, I have 1. Plus there's a coefficient, I will leave the coefficient. A draws by 1, I have 3. B increases by 1, I have 2. Plus there's a coefficient. A draws by 1, I have 2. B increases by 1, I have 3, right? And then plus there's a coefficient here. A draws by 1, I have 1. B increases by 1, I have 4. Plus there's a coefficient here. A draws by 1, I have 0. A must move from 5 to 0. That's when I'm done. And B must move from 0 to 5. So I have B to power 5. Alright, so this is what Pascal triangle does for you. It gives you the coefficient. So I can now come back to this setup. I can now build this setup and see. This is 0, 1, 2, 3, 4, 5. I will now go to the coefficient of when it is a plus b to power 5. When it is power 5. Remember, the count is 0, 1, 2, 3, 4, and then 5. 5 will be 1 here, because from here I drop 1. 4 plus 1, 5. 6 plus this, 10. This plus this 10, this plus this 10, and then when I exhaust this, I drop 1. This will be the coefficient I will compute here. So the first coefficient is 1, the second coefficient is 5, the other coefficient is 10, the other coefficient is 10. Okay, so sorry, this is 1 plus 4 is 5 rather, not 10. So 1 plus 4. So the other coefficient is 5. The other one is 1. So that is what Pascal triangle does for you. It doesn't really give you the full expansion. It only gives you the coefficient of the expansion of each of the terms of the expansion. And with that, I can now say this is 1 times this times this. I have 1 times a to power 5 times b raised to power 0 is 1 plus 5 times a to power 4 times b to power 1 is b. B to power 1 is b, right? Plus 10 times a to power 3, b to power 2, plus this one, this is 10 times a to power 2, b to power 3, plus 5a to power 1, 5 times a to power 1 is a, b to power 4, plus this is 1 times a to power 0 is 1, b to power 5. I can now simplify this. If I simplify all of this, I have a to power 5 plus, if I simplify this is 5a 4b plus 10a cubed b squared plus 10, okay, let me write it down here, 10a squared b cubed plus 5ab4 plus b5. Okay, that's just the expansion of that. So the concept, the idea of Pascal triangle, like I want to tell you, is that it only gives you the coefficient. It only gives you the coefficient. And remember, this is the same thing as if I'm talking about 6 combinations, for example. If I'm talking about rather to power 5, for example, if I'm talking about to power 5, this is the same thing as 5 combination 0. This is 5 combination 0, 5 combination. Okay. Okay, so that's this 0 factorial over 0 factorial. 0 minus 0 factorial, this is 0 factorial, 0 factorial, 0 minus 0 factorial, 1 over 1, this is 1. Okay, this basically is 0 combination 0, right? So this is 0 combination 0, and this is 1 combination 0, 1 combination 1, because the power here is 1. For this power 2, this is 2 combination 0, 2 combination 1, 2 combination 2. All right, this is 2 power 3, 3 combination 0, 3 combination 1, 3 combination 2, 3 combination 3. So basically, this Pascal triangle gives you the value of the combinations, which is the coefficient of these terms. All right. Okay, so this is the binomial expansion of positive integer index. In the next class, I will discuss binomial expansion of negative integer index, and then we'll also discuss binomial expansion of fractional index, and then we'll now solve general examples with kind of a bit higher difficulty as compared to this one we've done. We'll do a general exercise with complex examples where you see how to expand binomial expressions. All right, if you enjoyed this video, do well to like and subscribe so you get notifications when I upload new videos. And you can check out other of my videos, more of the videos I've uploaded. You can go through so you keep learning.